Here at the University of Cambridge, ICCS, which stands for the Institute of Computing for Climate Science, is making breakthroughs. I'm here with Dr Laura Cimoli, a research fellow at ICCS.
Hi, Alexandra. Thanks for having me. My expertise is physical oceanography, which means that I study the physics of the ocean. So I'm interested in knowing how, for example, different water masses form, what sets their properties, and in general, how does the ocean circulation work and its variability.
I asked Laura why it's important to study the oceans.
The ocean has been playing a big role in regulating the climate system. For example, we know that it has taken up, if we want to sequester, removed from the atmosphere about a third of the anthropogenic carbon emission. So that's the carbon that it is in the atmosphere because of human emissions. And it has also taken up a lot of the warming that these emissions have caused. So basically, without the ocean, we would already have experienced a much warmer climate.
If you're looking at the big changes, do you still have to represent smaller scale things that are going on, and how would you do that?
Yes, you do, and how you do that is a very big question. Imagine a model of it as a pixelized, if you want, image. And so if the more pixels you have, so the smaller your grid is, the better you will represent that image. But a lot of times, again, we run into a problem of computational cost. So we cannot have a super fine resolution everywhere. I don't know, think about a picture of a face, and if you know that the person has a spot somewhere. But if the image is very blurred, you don't see it. And it's a similar, so think about an eddy now in the ocean. It's like a small spot, if you want, when you look at the whole basin. So we won't be able to see it if the model resolution is not high enough. The problem is that we do care about those eddies, for example, or in general the smaller scale processes, because they do contribute to, for example, exchange heat or exchange carbon or nutrients and oxygen. So we do want to represent their impact on the climate system. And this is when we use what we call parametrization, which is a way to represent the effect of these smaller scale processes, which we don't really represent, onto the larger scale flow.
You've just heard from Laura why it's important to include small-scale processes in your climate model. She says that parametrizations are a good way to go. Someone who can explain this well is Dr Jack Atkinson. He's a research software engineer and does this for ICCS.
Within our computer models, in the ideal world, we would model things down to sort of the individual raindrops, or maybe even the individual molecules of water. But if we're talking about the whole globe, or even, say, an entire cloud, that's not really feasible. So what we're doing is maybe modelling things in terms of boxes of air which contain water vapour. And so in that instance, we need to find some way of representing the physics that goes on with that air, with that water vapour, that gives us sort of the correct net physical results, but doesn't require individual modelling of all of these individual molecules, atoms, whatever. And so that's often done through what we call a parameterization. So the idea is that based on the things we know, so maybe the air temperature, the pressure, the humidity, we know that under sort of certain parameters, a certain amount of this water content will be transformed into liquid water or raindrops, a certain amount will remain as water vapour, and if a certain amount is transformed to liquid water, we know that will sort of release a certain amount of energy, and that certain amount of energy will impact the temperature. And so by sort of developing these equations or these relationships for the substances in that entire box, we can get the right outputs. Another one people often talk about is with clouds. So clouds can be anything from sort of tens of meters to kilometers if you have a big thunderstorm. But if we're dealing with boxes in our model that are also tens of kilometers big, you can't represent each individual cloud. But the challenge here is that you also can't average that cloud across the entire box, because the behaviour of sort of small wispy clouds is going to be very, very different to if they were all lumped into one big storm cloud. So another place we use parameterizations is sort of within cloud schemes and understanding what happens under different conditions.
So parameterizations are used to deal with these small-scale processes. Now back to Laura. Why is it that we need to work on different components of the climate system separately? Why can't we just make one model with everything?
Well, we try to have one model with everything, and we had different, what are called coupled models, which means that they couple all the different components. But it is then harder to represent really all the processes at once. Like the feedbacks we were just talking about, it's hard then to represent all the multiple feedbacks that are actually happening. In some cases, we might not even know the equations very well that we want to represent. And in many other cases, we have computational limitations. So we cannot have a fully coupled model at high resolution, horizontal and vertical resolution, just because we don't have a computational power. And in a lot of cases also, we don't have the observation to necessarily validate all the processes. All of these components, again, interact together in complex ways. So a lot of times to understand actually one process, like how does it actually happen, how does, for example, again, the dynamics of the ocean work, what forces it, what are the different processes happening at the multitude of scales, then it's hard to do it in a coupled model, and it's very computationally costly. So we then split basically different models also into different components and look at each of them independently.
And what would you say is the most challenging part of your work?
My work really focuses on the deep ocean, which means everything in the bottom 2 kilometers. And if you think about the ocean, is on average 4 kilometers deep. So I'm really looking at the bottom half. And honestly, here there are so many challenges because it's a part of the ocean where we really don't have a lot of observations. Most of the observations are still based on ship measurements, which means you need to go out at sea on a ship and measure locally what's the physical and chemical properties. But we still don't have a basically autonomous float that can measure it almost in real time for us. And models also don't do a good job there because we don't have a lot of observation to constrain them, but also because the waters that fill up actually most of the ocean form in very small regions in high latitudes, so either near Antarctica or in the North Atlantic during winter time. So we don't have basically any observations, or very rarely we have observations during when these water masses are formed. And then they flow in regions of the oceans where it's very hard to measure. So there is a lot of technical challenges basically into understanding what is happening in the deep ocean. And consequently there are still a lot of unknowns. So what drives the dynamics, what's the natural variability of these water masses. And we know they have been changing because, again, already of climate change. But it's also very hard to draw the line between what is natural variability and what is not, because, again, we don't have a lot of observations. But that makes it also fun. There's a lot to explore.
As we've just heard, climate science can get quite complex quite quickly. Jack, our research software engineer, has a multidisciplinary background in fluid mechanics with applications to the atmosphere, and that led him to do some postdoctoral research on volcanic plumes, including their interactions with different microphysics like ice and water.
I then went to the Antarctic Survey, where I worked with the radiation belts and the space weather group, so looking at electrons and the way electrons behave, sort of following solar storms in the Earth's environment. And then following that, I moved to the ICCS. So all my work has involved numerical work and numerical modelling and processing data. So a big part of it was kind of dealing with software, in particular research software, and it was something that was always on my mind, was sort of writing good code and writing careful code. And I started paying more and more attention to kind of helping others and sharing knowledge, enforcing sort of good practices. So when the role with the ICCS came up, it was something that I was interested in pursuing, but also kept me very much in touch with the atmospheric science that I really enjoy.
What actually is good practice when you're programming?
The big one is probably testing. So there's this idea that if you write a huge piece of software, sort of at the extreme, you might say one of these big climate models, you want to know that all the little bits of that are working correctly. And so the idea is that as you write some code, you should also write some tests just to check that everything is working before you put it all together. So at the most simple level, suppose you had something that added two numbers. You wouldn't just write it and hope that it added two numbers. You'd actually write some tests to say, if I give this 2 plus 2, does it give me the answer 4? If I give it 10 plus 10, does it give me the answer 20? And that way I can be sure that when I implement it into bigger projects, it's all working as I expect it to. The other big one, I think this is one that ICCS and the VESRI teams are pushing for, is open software. So this is the idea that rather than kind of keeping all your code, all your software, everything behind closed doors and being very cagey about it, it's actually putting it out in the open, which of course does open it to scrutiny, but that's not a bad thing, because often you will find people who want to help, want to make that better, want to work with you, and it's, I think, is a big thing for trust, and that's something that we definitely need to think about, especially within the climate modelling community, is making sure that people do trust the work we're doing.
Jack just mentioned working with the VESRI teams. Those are the Virtual Earth System Research Institute groups, and they work on specific climate models. All of the RSCs, or research software engineers at ICCS, work with various different VESRI teams to help them make their code as good as possible. Now Jack will tell us about one of these collaborations with DataWave, and it looks at gravity wave research.
DataWave is looking at gravity waves, which are waves within the atmosphere. If you have air and you move it up in the atmosphere, it will be more dense than the air it's around, so it will drop back down. But then as it drops back down, it will move to where the air is more dense, and so the blob of air is less dense, and so it'll move back up. So it will sort of oscillate around. So that's the kind of really simple gravity wave. And then this is parameterized, and DataWave are looking at kind of developing a few different approaches to improve the modelling of gravity waves because they're important to climate models. So we looked at it from sort of two routes. One was, can we actually make it kind of more computationally efficient, so faster data transfer and all of this stuff, but also from the other side of kind of development and the actual scientist software developer time. The way they've been doing this was using something called 4Pi, which is nominally quite a nice little library. So actually, I guess to backtrack, the important thing here is that their machine learning was written in Python, because you have PyTorch and TensorFlow. They're very nice. It's very easy to use. They've got lots of functionality for machine learning. And the MEMA model was written in Fortran, which is faster, a much more efficient language. It's what a lot of big climate models are written in, and you don't want to kind of rewrite entire models. So the difficulty is sort of doing your machine learning computations in Python and then passing that information to the big model in Fortran back and forth. So one approach was, can we make it faster just in terms of sending that data between the two and sort of running your calculations in Python, which is typically a bit slower, but also in terms of the time that the scientists have to spend connecting these models, sort of the learning curve they have to go through, learning how to couple these things, the computer science side. Sort of, is it possible to make that process much more simple, especially because this is something that a lot of groups are going to be trying to do. So there's something called Smart Sim, which does sort of data transfer. So this will be quite nice. It will allow you to kind of package up the data from Fortran you need, pass it out, send it somewhere, do some Python, pass it back. But in sort of software computing, taking copies and transferring data is always very, very expensive. So if you don't have to do that, sort of you don't want to. So it turns out that PyTorch actually provide a really nice sort of what we call an API, so application programming interface, written in C++. So this allows you to kind of access all of your PyTorch stuff, not through Python, but sort of through this underlying level of C++. And it's much, much easier to use C++ from Fortran than it is to use Python. So we took kind of the existing C++ interface and then sort of developed a library that sort of just wraps around that. So to you, it looks like you're calling a Python function, but really that Python function just calls a C++ function, which calls the underlying torch. The advantage there was that what we could also do is, rather than copying all the data, you can put the data in your memory on Fortran, and instead of saying sort of take a copy of this and create a Python object, you just say, here's all the data stored in memory, I'm going to tell you where it is, and you can look at it and pretend it's a Python object. So we did this with Mima, we sort of put it back in, did some testing, and that's now gone to sort of, it's been left with DataWave. They've now got this model that's coupled, and then hopefully as they build other machine learning models possibly in Mima or in other codes, they will now have something that they can couple it with. And of course they can come back and ask us for help. And what we've now done is sort of ICCS has taken ownership of that kind of sub-project, just the pure coupling, because it's something that's likely to be important to sort of several different groups. And so we're continuing to build on it, and we've had interest from sort of other people in the Vesri, but also a couple of groups from outside.
Jack's explanation has just showed us that there are lots of different programming languages involved in climate modelling, and sometimes it's not only about making it more efficient, but easier for the climate scientists themselves to use. According to Laura, the research software engineers are extremely helpful.
They're a great team to, again, support us to basically make the best also of our science, right? So everything is done with the best software practices, which means that ultimately my work is becoming so more efficient, more easily transferred to the rest of the community. Also in terms of, the findable, reusable resources for the community, all of that is done much better thanks to the support of the research software engineers.
And to round off the episode, we'll hear from Jack about why the Institute of Computing for Climate Science is important.
Yeah, so I think, like we said, it's important because it's helping several of these other groups that are working in climate science to sort of combine talents or combine expertise to make the most efficient progress we can with their work. I also think it's important because there's the opportunity to have sort of a wider impact on the field as a whole and actually sort of tidy up some things that have maybe grown a bit unruly as sort of climate science has developed, moving into sort of ages of higher performance computing. And so to standardise or inform things in this aspect, I think it's still quite early, so it's only been about a year and we're still becoming a known entity, but hopefully that will continue and will become more recognisable and have more say. And I think we've already been doing a lot of work to kind of publicise our work, but not only publicise but also share with others and share with people across the UK and across the globe where sort of work that we've done and things that we might have that can help.
This was a one-off episode produced by me, Alexandra Higson, a communications intern at ICCS. I interviewed Dr Laura Cimoli and Dr Jack Atkinson. If you enjoyed listening and would like to learn more, you can head over to our website at iccs.cam.ac.uk and follow us on social media. We also share technical information, presentations, and workshops on our YouTube channel. Goodbye!